We now describe the general method for deriving reliability-based partial safety factors used in design. But I'd like to emphasize what I have said before, that a design standard is much more than just some design equations. It is a collection of wisdom and experience from successful performance that have accumulated over generations. So we are not going to look at all those aspects, of course. We are just looking at this very narrow issue of partial safety factor to be used in design equations and how we can derive them, at least the principle behind them. There are also many issues, and again, we should not trivialize them. And I have listed a few here that the design obviously is governed by and has to be consistent with the geometry of the structure or the member, the material to be used, or materials to be used, and construction method, construction technique. Obviously, we have been talking about this. What are the limit states? How the limit states are defined? What is the underlying mechanics? What are the target reliabilities? We still haven't talked about how they are derived, how we know what is safe or how safe is safe enough. So that's also a major consideration which we are living out for today. Then how our loads are defined. Are we taking a physical definition? Are we talking about nominal loads? Are we talking about statistical description? So these things have to be clearly understood and separated. The design equation itself, what format? There are many equivalent formats, but each will have different outcomes. So we must understand, we must decide unambiguously what the verification space is. Is it in terms of stress or strain or moments or forces, etc. So we need to be able to make sure that that aspect is well defined. Which load combinations, which ones are relevant, they have a direct bearing both on the limit state and the design equation. And then what sort of structure or structural member are we going to, or is this design equation going to be valid for? And then coupled with that is what sort of analysis, both probabilistic analysis and mechanical analysis, should be ensured in order for the design equation to be valid for the structure or the member being designed. Now that said, let us describe the steps that can be followed in general for developing design equations for common structures. Again, we are talking about structures or members with whom we have enough experience, and at least we know what works and what doesn't work, and we have a clear understanding of what constitutes satisfactory performance and what does not. So clearly we want to derive a design equation that is valid for a number of structures in various design situations, provided they are of the same type, of course. So we decide on the type of the structure and then on the scope of the design. Then we carefully select representative structures from this type that cover the entire range of design situations that we are interested in. Following this, we could perform what is known as a calibration exercise if we do not have an independent knowledge of what reliability we should aim for when we derive this new design equation. So so part of that calibration exercise, we perform reliability analysis on these representative structures, stored them, and based on that analysis, which also requires all the uncertainty information, we decide on what target reliability or target reliabilities we should go for in our new design equation. And then we start a loop after we know the design equation format, which depends on the scope of design that we already discussed. Then we start this loop of tweaking or optimizing the partial safety factors. So with the design equation format given, we have a trial, and then we design those same representative structures that you see on the top box, and then the reliabilities that we get, we compare with the target reliabilities, which were either obtained by calibration or other more direct means. And then if those are acceptable, then we are fine. Otherwise, we keep adjusting, and that's the optimization loop, until we are happy with the outcome. All the optimization constraints have been satisfied. Now, focusing on these PSFs, so this is what we want. The set of PSFs should ensure satisfactory reliability for all the R design situations. By design situations, we mean the either different element groups, different loading configurations, etc., etc. In our cable example, it was basically possible values of Wn over Qn. So each of these design situations, R of them has their own importance. So if we have to see how well our design equation is doing, we might weight that with the importance factors there. So the mathematical statement is find the partial safety factors, phi's, and the gammas such that a certain error is minimized. So the error is the weighted deviations. So I find beta I for design situation I or element group I, and then take the deviation from the ideal target, square that, and weight that with the importance factor. And it's sensible to say that the weights are normalized, so they sum to 1. So that is our objective function: minimize the weighted sum squared error. And then obviously we could put constraints, and that comes from our level of comfort, our engineering judgment. So it could be that whatever optimal solution we get, we will not let any single beta go below the target over a certain amount. So we could fix delta beta, and no beta I should be less than delta beta below beta target. We could put more restrictions on the phi's and the gammas, and that could be, obviously they should be non-negative, but for the phi type factors we can say that we don't like them to be more than 1 because they are strength type factors, and we don't want them to be more than 1 since we would like to reduce the strength in design. So, and then the loads, we could likewise say that we don't want to be less than 1, they should be at least 1, and that agrees with our intuition that load factors should amplify the loads. And then obviously if these two limits are both equal, then we are essentially fixing the value of phi or gamma at a particular number, and that is also quite acceptable. If we want a load factor or a set of load factors coming from some other document which are well researched and well accepted, then we have no reason or no scope to optimize them. We have to choose them as they are. We have to take them as they are. So for those we could fix their values, so gamma min and gamma max will be the same number. So, and obviously this sort of error which is the weighted sum squared, it doesn't have to be that way. We could give an unsymmetrical weight to higher values versus lower values, and there are many options, but the principle is the same. With this, now let us go through a problem involving the load and resistance factors for the design equation of a ship hull girder or ship hull girders.